Okay, so we're going to spend the next two sections in Chapter 7 looking at what we're calling operational properties of the Laplace transform. And what these are just certain properties that the Laplace transform has that are going to be useful in applying the Laplace transform to a more broad selection of DEs. So to kind of just jump right in, we're going to start with something that we're calling the first translation theorem. So let's suppose that we have some function f of t and its Laplace transform is capital F of s using the usual notation that we use. And if a is any real number, then the Laplace transform of e to the at times that f of t is equal to capital F of s minus a. In other words, evaluating this Laplace transform can be done by simply substituting s minus a, this a here, into the Laplace transform for just f of t. Okay, this one's very easy to prove. If we wanted to evaluate the Laplace transform of e to the at times f of t, directly, then this is what that would look like using the definition of the Laplace transform. But because we have two exponential functions that are being multiplied here, we can combine them and we get e to the negative quantity s minus a t here. Now, this thing looks a whole lot like the Laplace transform of just f of t, except we've substituted s minus a where there would normally be an s here. And so the result of this is going to be the same thing as capital F of s minus a, same substitution in capital F of s. Okay? So essentially what this does, if you remember if you have a function capital F of s like this and you substitute s minus a in there, then what this does is it translates the function capital F by a units. To the right if a is positive, and to the left if a is negative. And so that's what we're seeing right here. Okay, if this is capital F of s, then capital F of s minus a is going to take that exact same curve and translate it a units to the right in the case where a is positive. So that's what the effect of multiplying f of t by this exponential e to the at and then taking its Laplace transform does. It translates that Laplace transform by a units. Okay, and that actually makes a number of what would normally be difficult Laplace transforms much easier to evaluate. So let's take this guy for example. Oh, and before we do that, I want to look at some notation that's going to be useful for us here in this section. So because we have this translation property, which allows us to basically just substitute s minus a in for s in our Laplace transform. The notation that is useful here is this. The Laplace transform of e to the at f of t is equal to just the Laplace transform of f of t, where s is swapped out for s minus a. So this little vertical bar with this s pointing to s minus a is saying that once we evaluate this Laplace transform and get that function of s, we're going to substitute an s minus a in for the s that would normally be appearing there. So here, we want to evaluate the Laplace transform of e to the 4t sine of 5t. Notice this takes this form. It's an exponential times some function of t. And so using that notation, I can write this. The Laplace transform of e to the 4t sine of 5t is equal to the Laplace transform of just sine of 5t, where the s that's going to appear is going to be swapped out for s minus 4. 4 coming from my exponential function. That's what the a is. Okay. Now, I know this Laplace transform because it shows up in our table. So normally this Laplace transform would look like k, which in our case is 5, over s squared plus k squared down here, except instead of s squared, I'm going to write s minus 4 squared. Okay, plus k squared, which now is 5 squared, or 25. Okay, so you can see how quickly I can evaluate what would have normally been kind of an intimidating Laplace transform by using this property. It's extremely, extremely efficient. All right. Now, we can't talk about the Laplace transform of a new type of function without also talking about the inverse transform, because we know that when it comes to solving DEs, we need both of those things. So in this case, just working the first translation theorem backwards, if I have some function that can take the form f of s minus a real number a, and I want its inverse Laplace transform, then this function, capital F of s minus a, is the same thing as capital F of s with this notation where s is swapped out for s minus a. And according to our first translation theorem, this should equal e to the at f of t. Okay, so let's try evaluating an inverse Laplace transform using this. Now here I have 5s over s minus 2 squared, and as we've now seen plenty of times up until this point, in chapter 7 we're doing a lot of partial fraction decompositions. I'm gonna skip past the work of evaluating this directly, even though this is a very straightforward one. Here we have 5s over s minus 2 squared is equal to where did I have it? 5 over s minus 2 plus 10 over s minus 2 squared. Okay, so you would find this just by doing a normal partial fraction decomposition, and you can verify by adding these to get back to this to see that this is the correct decomposition. So what this means is that if I want to evaluate this inverse Laplace transform, this guy, 5s over s minus 2 squared, that's the same thing as evaluating this inverse Laplace transform, or really this linear combination of inverse transforms. 1 over s minus 2 plus 10, I'm just using linearity here, 1 over s minus 2 squared. Okay? Now this guy right here, we can find directly. This is straight from our table. We know that this is equal to 5 e to the 2t plus 10 times this guy. I don't have anything in my original table of Laplace transforms that looks exactly like this, but it's pretty close to something that does appear in our table. If this were just an s squared down here instead of an s minus 2 squared, I could match that to a function in my table. And so what I'm going to do is rewrite this way. 1 over s squared, but then I'm going to write that notation where the s is then swapped out for s minus a. No, sorry, not a, 2 in this case. We have an actual number to use, 2. So you can see if you put s minus 2 in for this s here, I get back to this guy. But what is this equal to? Well, 1 is equal to 1 factorial, and this is the this is the Laplace transform, the thing on the inside here, of just the function t. Okay, check your Laplace transform table to see that. So this will then be equal to 5e to the 2t plus 10t, but then because there's a translation happening here, 2 units to the right, the first translation theorem says that this also gets multiplied by an e to the 2t. So again, I matched this guy with my table of Laplace transforms, or inverse Laplace transforms, to get a t, and then the translation that's occurring to simplify this to this requires me to put this e to the 2t here by that first translation property. Okay? So again, that was a pretty efficient way of evaluating that inverse Laplace transform by using that property. Let's use this idea, this property, to solve an actual differential equation now. So I'm going to try and solve this IVP here. It's the second order, y double prime minus 4y prime plus 4y equals t cubed e to the 2t. And my initial conditions are y of 0 equals 0, y prime of 0 equals 0. Okay, so as we've been doing, I'm going to take a Laplace transform of both sides, and I'm going to use linearity. So we're going to get the Laplace transform of y double prime minus 4 Laplace of y prime plus 4 Laplace of y equals the Laplace transform of t cubed e to the 2t. Okay, now right away I can see that this is going to make use of a translation because of this this factor of e to the 2t occurring here. So I can also write this last term here as the Laplace transform of just t cubed, where s, there's my vertical bar there, is substituted out for an s minus 2. Okay, so that's going to allow me to evaluate this using that property. All right, now what would this left-hand side look like? Well, we know that this guy is going to equal s squared times capital Y of s, Laplace transform of my solution, minus s times y of 0 minus y prime of 0. That's this first transform. Minus 4 times Laplace transform of y prime is going to look like s capital Y of s minus y of 0 plus 4 times the Laplace transform of y is just capital Y of s. And then on this side, I need the Laplace transform for t cubed. And what is the Laplace transform for t cubed? Well, that's going to look like 3 factorial over what would normally be s to the power of 3 plus 1, or s to the 4th, except we're substituting that s out for an s minus 2. S minus 2 to the 4th. Okay? Let's simplify this down. So the initial conditions in this case are really convenient because both y of 0 and y prime of 0 are both equal to 0, meaning all of these guys are just going to 0 out. That leaves me with s squared y, capital Y, minus 4sy plus 4y. Each of those 3 remaining terms has a capital Y of s in them, so I can factor that out. That's going to give, I don't want equals, I want that to be like this. S squared minus 4s plus 4 equals 3 factorial equals 6. S minus 2 to the 4th. Okay, now notice this guy right here factors, so I can write that as s minus 2 squared equals 6 over s minus 2 to the 4th. And then solving for capital Y of s, I'm going to get y of s equals 6 over, divide both sides by s minus 2 squared, and I'm going to get s minus 2 to the 6th power. Okay, now prior to learning this translation property, normally what you would be doing is trying to find an inverse Laplace transform of this guy, which would require a partial fraction decomposition, and because that's a 6th power there, that would be a fairly ugly partial fraction decomposition. But we can save ourselves a whole lot of work by writing this way. 6 over s to the 6th, where s is substituted out for s minus 2, okay? And this is pretty close to something that already appears in our table of inverse transforms. So I can avoid any partial fraction decompositions by working directly with this instead. Now, it doesn't exactly match what we want. Remember, what we want is n factorial over s to the n plus 1 power down here. If I have a 6, then n would equal 5 plus 1. So this should look like a 5 factorial, which means I want to write this as 6 over 5 factorial times 5 factorial over s to the 6. And again, where we have that substitution taking place. Okay, this guy I can find the inverse Laplace transform of directly. So if I took the inverse Laplace transform of both sides, I'm going to get y equals the inverse Laplace transform of this, which is equal to 6 over 5 factorial. The inverse Laplace transform of this guy right here is going to look like t to the 5th, right? And because there is a translation happening, I also have a factor of e to the 2t showing up there, okay? Notice that could have been a much longer problem if we were dealing with partial fraction decompositions instead of using this really, really useful property. So I'm going to stop this video here because in the next video we're going to talk about a second translation theorem, so it's kind of a natural break at this point.